I guess I'll just say I went to the TWiML a couple of days ago in San Francisco, and it was really a terrific conference organized by Sam Charrington. It was all about the productionizing models and at large scale, the way it's done in large corporations. So there were representatives from a lot of the big companies like Twitter and I can't think of all of them. There were a lot of the big companies were represented, and their people gave talks about how they made sort of end-to-end systems. I guess they call them. The conference was themed. The theme of the conference was platforms, and what they mean by a platform is a complete end-to-end environment for building and productionizing models. And so, each of the large companies, Facebook, Twitter, et cetera, they all have their own way of doing this. And in some sense, it's specialized to their own needs. But you can see that the community is grasping towards sort of a very general framework that can be customized for anybody that wants to use it. And maybe that's coming out. Maybe they'll reach that in the next few years or so. But meanwhile, each company seems to have developed their own platform. So it was really interesting to see people talking about that and hear and see the progress that they've made. Okay, well, we now have.
This is Joseph speaking.
Yes.
Oh, okay. I recognize you from your voice. So, is any material from the conference available online where we can see?
I think they will. I think they will make those talks available. Already, Sam has put some of the talks on his TWiML podcast. They've come out in the last couple of days, and some of the panel. I guess he, as part of the conference, he actually did live podcasts with several interesting people, and those I think have already come out. But I think that he'll make more of the material available because people have asked for slides and so on. And so I guess keep in touch with that, with his website, the TWiMLcon website, sorry, the TWiML website, and you might see these things coming out.
Yeah, okay, I'll watch out for it.
Okay, great. Let's see, any other remarks or questions that anybody has? Has anybody tried to keep up with Jeremy's Fast.ai version 2 walkthroughs?
I tried it, but like I was not getting most out of it because I've not done this part 2. I've not completed it yet, even once.
Yeah. I found it hard going. I went through the first 4. I think I'm going to keep trying, just listening to them again and keep going through. But they're pretty dense, it's true.
Yeah.
But after the struggles that we're going through with this part 2, we should be in good shape to at least get most of what's going on in those walkthroughs. So, all right. So let me just start. Okay, so today I want to finish lesson 10, which is mainly that last notebook, the 07 batch norm notebook. And then for the next meeting, we'll start lesson 11, and we'll try to go through some of the following notebooks, the 07A, the 08, and the 09. I think these notebooks they're less involved than the ones we've been through in chapter 10, so we might be able to get through all 3 of them, but we'll see. All right, let me share the notebook screen. Let's see. Start sharing. I want to share. Okay, is everyone seeing the batch norm? The batch norm notebook now?
Yep.
Okay, great. So I didn't do very much with this notebook as far as annotation, but I did. There are 5 main pieces. One is the review of the convnet, like he did in the last notebook. Then he moved to developing batch norm from scratch, which we do here. And then he discusses generalized kinds of norms. So there's batch norm, there's layer norm, there's instance norm, and there's group norm. We'll get to discussing all those. And finally, and then he tries out some of those and discusses them a little bit. And then he invents this new thing called running batch norm that fixes, let's see, did I get this numbering right? Let's see, 3, yes. So the 4th thing he does is he develops this new thing that's unique to Fast.ai called running batch norm, where he fixes the problem with small batch sizes. And we'll talk about that. And then finally, he just challenges us, how well can you do in with a single epoch? And I didn't play with that, but I intend to. Anyway, so let's go from the start. So just reviewing what we did before, we first load the data for the MNIST data set. That's what's going on here. We then normalize the validation data, remember, to the training data. And what that means is we're using the mean and variance of the training data to normalize the validation data. So that's what's going on here. And then he defines the number of hidden layers and the batch size here. And the number of digit classes is 10, and that's just the, let's see, the max plus 1. The max of Y train, the labels go from 0 to 9. And so the max of that is 9, and then you add 1 is 10. That's what C is. C is the number of digit classes. And then the loss function we use, remember, is the cross entropy loss. And then finally, having defined all of these things, we can create a data bunch. And that's what's done here. So this is just a review of last time. Then we get we make this callback function to resize a flattened image. Remember, the input data comes in 1 by 728, I think it is. No, 700, I remember.
784.
784. It's 28 squared. So the input data, each image is flattened in the input data. So this is a little function that, it's a little callback function that restores it back to a 28 by 28 image. And so now he makes a list of callback functions. And this is the same list we had before, except now he's adding this one with the NIST view function in it. So, okay, then the number of then we define the number of channels for each convolution layer that we want. So the first layer has 8 channels, then 16, then 32, then 64, then 64. Then we construct the learner and runner objects for the model, and it takes as input this NFs and the data bunch that we created, and the 0.4 is the learning rate that we want. Conv layer is a function that we defined in the last notebook that actually builds the convolution layers from the input specifications. And the CBs is the list of callbacks, which we defined up here. Okay, so then we run the model for 2 epochs, and we see that we get to something like, validation, 87% with the validation set. So it's working, but not that great. So the next thing he does is he defines this batch norm, and we should look at let's see, I wonder if I think I did this. Well, he's got it here down at the bottom. Okay, so this is we might as well just use this formula. This is the batch norm, the way it's defined, and it looks awful, but really it's not as awful as it looks. So what is this YTIJK? TIJK. So we should keep in mind, this is the key to this whole, to understanding this whole thing, is to understand what this four-dimensional X looks like. And the four-dimensional X, the dimensions are T indexes the sample number, that is the the sample of the digit, right? So remember that our database has something like 50,000 training examples in it, and so T indexes the sample number, I indexes the channel number, J and K index the two-dimensional weights matrix that's associated with this example. So he calls it H, and elsewhere he calls it H and W. There's I think this, let's see, somewhere there's a drawing up here. Here, and so N is N corresponds to the T, which is the and I don't know why he uses T, but it's basically indexing the sample number along this row. C indexes the channel number, and then HW, there are two different dimensions, and he's representing them as a single dimension here, but that's okay because it's kind of like it's the two-dimensional weights array.
Height and width.
Height and width, yeah, it's the height and width of the two-dimensional weights array. So height and width, you could think of height as the y direction along the two-dimensional array, and W you can think of as the x direction along the two-dimensional array. So he's chunking them together as a single thing because you can't draw a four-dimensional picture. So so this is okay, because whenever we consider H and W, we're always considering it as just a single thing, the two-dimensional weights matrix. Okay, so the batch norm, what he's doing is he's averaging over the samples in a batch for each channel. He's averaging the weights matrix. He's basically averaging the weights matrix over all the examples. So if we had one example, it would just be the average of the weights matrix. If we have, if we had one example, it would just be the average of the entries in the weights matrix for that example. If we had two examples, it would be the average, the average over all the weights matrix for both of those examples, and so on. Okay, so is that clear? It's each weights matrix is 28 by 28, or actually no, I think it changes as you go, because the input image is 28 by 28, but then that image gets mapped into by all the convolution layers as you go through it gets mapped into different dimensions in the weights matrix. So for batch norm, you're working by each channel. You're averaging all the weights matrix for all the examples in the batch. Okay, back to these indexes. Where are they? Sorry, I'm scrolling a lot here. Yeah, so here's the the initial thing. The X TIJK. Remember, the T indexes the sample number, the I indexes the channel number, and the J and K index the weights the dimension, the height and width in the weights matrix. And so for batch normalization, you're averaging over you're averaging the mean, and the mu here, this Greek letter mu is the mean. It's the mean of all the weights matrices in over a channel, in one channel. So it's like that. I should go back up here, or back. Is it back up or down? Yeah, it's up here. So here's the picture of that. Here's one of the channels, and we're averaging all the weights matrices in all the examples in the batch for that channel. So n is the number of n is the number of n is the number of examples in a batch. Okay, so in this case, I think we defined it as 512. So yeah. So let's see. I'm just looking at this thing. This is kind of like a general expression, what's going on in the batch norm, although he's applying it to layer norm here. We're subtracting some kind of a mean. We're dividing by some kind of a standard deviation, which remember is the square root of the variance. And here we're adding this little epsilon to make sure that that when the variance is small, that it doesn't blow up. So that's what that epsilon is. It's not. It's usually set to, in Fast.ai, it's set to 1 times 10 to the minus 5. And its function is basically to prevent this thing from blowing up when the variance gets small. Because you can imagine if the variance becomes 0, for example, then the denominator would be 0, and this thing would go to infinity. But with epsilon in place there, it won't ever go to infinity. Okay, and then this gamma, this Greek letter gamma, and the Greek letter beta, these two things, Jeremy doesn't like Greek letters, so he calls this mults. Later on, he calls this mults. And he calls this adds. Beta is adds. So beta is basically an additive parameter and an offset parameter that acts like a bias. And that's why, since that's included in batch norm, that's why you turn off the biases when you run batch norm, because this beta parameter has the same function. Actually, beta isn't just a single parameter, it's a whole array of parameters. And gamma, likewise, is a whole array of parameters. It has the same dimension as x. So remember, x was 4-dimensional in this problem, and so is gamma, and so is beta. Gamma, again, is multiplicative, is like a scale parameter. And so Jeremy calls that in later, I guess in the code, he calls it, instead of gamma, he calls it mults for multipliers. So let's just remember that. So, so let's see, what can I say about this? This, if you just look at this part here, without everything other than what I've got outlined and what I've got highlighted. In other words, everything to the left of what I've got highlighted. This is basically a normalization. You can recognize that, right? Because when you normalize data, you subtract the mean and divide by the standard deviation. But this has been found to not be adequate, and so, well, this is an improvement. Using the gamma and beta on top of that gives you an improvement to the ordinary method of normalization, and that's the batch normalization. So batch normalization is really solving for these learnable parameters, gamma and beta, or what he calls adds and mults. Mults and adds, I should say. So let's go back up to the batch norm, and now that we have that insight, we can look at it again. So here's what I mean by self.mults. It's, oh, what did I say? I said it was the same dimension as x, but I forgot that it's being in, let's see, we're averaging over channels, so instead of 4 dimensions, we have 3 dimensions left. And here's the adds. So these two parameters. And remember, when you say nn.parameter, that means you're defining a learnable parameter so that it keeps track of its gradients and so on, so it can update them and learn them. They get initialized to 1s and 0s. The mults are initialized to 1s and the adds are initialized to 0s. But then they're defined as learnable parameters. So in the course of training, you actually learn those parameters. And then he defines this buffer for, he defines this buffer for vars and means, which he's going to keep track of. and then so that's the initialization part. And then then he has this update stats part where he takes the mean, and this dimension is 0, 2, and 3. Remember, 0 is the sample, samples. Element 1 in X is the channels, and 2 and 3 are the weights, are the dimensions of the weights matrix. So he's taking a mean over these dimensions, over samples, just like we said before. This is a mean over the samples and the W and H in that diagram that we looked at before. And so when you do that, you expect it's just going to have the dimension of channels. I mean, the only thing that's going to be left is the channels. But keep dim equals true means okay, so for each channel, we expect that there's going to be one entry, one mean, because for each channel we're averaging over all the examples in the batch and over the weights matrix. So for each channel, we expect to have one number. But because we have keep dim equals true, the final dimension of this M and V are going to be this. We're going to have sort of markers for the sample, for the X and Y of the weights matrix. So does that make sense? We're keeping the original dimension of X, but the only entry is going to be in the channels dimension, because for each channel there's going to be one value of the mean and one value of the variance. So anybody, feel free to jump in and ask questions if they occur. I have no problem with that. Just unmute yourself and ask a question if you have.
Just to add over there, Joseph, that you're doing keep dims is equal to true is so that you can go ahead with broadcasting in the future.
Sorry?
The keep dims is equal to true kind of helps you with broadcasting in the future. That's why you want to preserve those dimensions, one number of channels.
Yes, that's right. Yes, because we're going to use M and V. We're going to multiply by them and so on. So we want them to have the same dimension as the thing they're multiplying and dividing. Okay, then the next part here is he's computing what he calls the exponentially weighted averages, exponentially weighted moving average. But all that is for us is just an interpolation between the last and next to last value. So this is actually this thing called LERP, means linear. I'm not sure exactly what it stands for, what the LERP, but I think it just means linear interpolation. And so when you do this means.lerp, all you're doing is you're computing each element is being computed from the last element and the next to the last element. And the last element is being multiplied by 1 minus the momentum. MOM is the momentum, which is usually in Fast.ai, they take it in this as the default value is 0.1. So this 0.9 is basically 1 minus 0.1. And then, so you can see what we're doing. We're taking some kind of a weighted average. We're taking, not some kind of a weighted average, we're taking a weighted average of the last value and the next to last value. And the last value is being weighted more heavily, but the fact that the next to last value is in there means that we're sort of preserving some kind of a memory of what went on before. But the second to the last value is weighted less. Okay, and the 0.1 is the value of momentum. So what this really is, or what in general, this would be, you could rewrite this as like this.
Isn't that supposed to be the current value, Joseph?
X, Well, yeah, that's right. I should have written it this way. Xj equals xj minus 1. That's the last value, and then xj minus 2, the second. Is that what you mean?
No, I mean, you use the last value and the current value. At least that's what I understood, because if you look at the line above, you calculate the mean, and then you're doing self.means.lerp m. So that's basically using that same m, and your means previously was set to zeros. So
Yeah, on the first one, on the first value, that's what would happen, right? Because it's initialized to zeros.
Mm-hmm. So it's basically 0 and the current value.
0 and the current value. So you mean you're replacing the current value with itself, with an average between itself and the previous value? Is that what you're saying?
Yeah, that's what I kind of, yeah, it's kind of confusing. You notated with an array, so I don't know if you hold on to those values.
Let's see. Does he say them? I thought somewhere he saved them, but maybe I'm wrong. So what you're saying is that you're replacing the current value with the current value times 0.9 and the second and the last value. This is what you're understanding. Like
that's
that.
what my understanding was. Yeah.
I see. So.
And again, like, I think, again, this is kind of confusing, but I thought you were retaining most of your memory and you're updating only like a small part of the current value. So it's kind of the other way around with the 0.1 and the 0.9. But again, that PyTorch uses it differently, Jeremy uses it differently. I don't remember which one is which.
I'm pretty sure that it's this way, but that's something we can look up for next time, or and make sure we get it straightened out. I'll just make a note to do that. Okay, so yeah, so I mean, you're most strongly using the current value, and you're less strongly using the last.
But then, like, for example, if your current value is 0, you don't want to be using maximum of that, right? You want to be using less of that and the maximum of the previous, your history.
Okay, I forgot where I found this, but now, okay, we'll need to get back on that next time. Let's touch base on that next time. But I just wanted to stress that the 0.9 is 1 minus momentum, and the 0.1 is the momentum. So in more general case, if you wanted to use different values, you would use 1 minus momentum instead of 0.9, and you'd use momentum instead of 0.1. But Prashant thinks that it's the other way around. So let's straighten that out.
He points out that in PyTorch, that momentum is the opposite of what you expect. So it flips it, like Prashant says. So
I see. Okay. Okay. So you're saying again that it's like this.
Yeah, because he talks about it that momentum of 0.1 in bench norm actually means momentum of 0.9 in normal English language.
Okay.
So, which means basically PyTorch flips the thing just like it flips on a linear, it kind of does the transpose. So similarly, in this case, I believe the values get flipped from what you would expect in an equation that you illustrate.
Okay, and my understanding of the flip was, instead of like a normal layman's term, you would pass momentum as 0.1, whereas on PyTorch, you need to pass it as 0.9, because it flips the 1 minus momentum and the momentum term to opposite terms. Okay, cool.
Yeah. But your understanding of how it works.
Yeah, I know that in this code, he uses momentum equals 0.1. So, yeah. I'll have to look up what it means to flip the meaning of momentum. I mean, because that's what I didn't understand when he said that PyTorch has the opposite of what you'd expect. I don't know what you'd expect. I mean, so I didn't understand that reference.
And what you expect is what Prashant was saying, which is, use a small fraction and keep a large fraction of what you had been averaging in the past. And that would mean the equation you've written, you keep a lot of the previous calculation and a small fraction of the current. So therefore you would give it, give the parameters as you have in the equation, but PyTorch flips it. Therefore, you need to accommodate that in what you specify.
Right. So what you are both saying, Srinivas and Prashant, what you're both saying is that this is the actual formula that gets used when we specify momentum equals 0.1.
Right.
Okay. Okay.
And when you say flip, to make that clear is you'll still get back the same formula. The only difference is now instead of passing momentum as 0.1, in PyTorch you would pass it as 0.9.
Oh, but you specify it as 0.1, and then PyTorch internally changes it to 0.9?
Exactly. And the way you're calculating, because all you're trying to do is you put one coefficient as momentum and the other coefficient as 1 minus momentum, right?
Yeah.
The way we are using it. So that's the flip PyTorch is doing, from my understanding. It's just flipping those coefficients. So that's why instead of passing 0.1 here, you'll be passing 0.9 over there.
Okay. So PyTorch, you give it 0.1, and then PyTorch interprets that to mean 0.9 in its own internal code. But what it means is that the actual formula, when you say 0.1, the actual formula that PyTorch is computing is this one.
Right.
Okay. And so more generally, this would be momentum and one minus momentum. So that, in other words, you can actually change momentum in the code if you want, and then what you'd get, you could make it more heavily weight the current measurement and less heavily weight the last measurement, if you want, by changing the value of momentum. And so this is essentially what it's doing. The 0.1 corresponds to the momentum, and the 0.9 corresponds to the 1 minus momentum. And yeah, so anyway, I don't think we need to say much more about that. So it's doing this, it's calculating this exponentially weighted moving average in this way using this linear interpolation formula. And then this part, I didn't quite understand why he needed a separate case to handle the training versus the evaluation case. So training, I guess he says with torch.noGrad, meaning that he doesn't want to keep track of the gradients of M and V. But then if you're not training, if you're doing evaluation, then he's not using this construct torch.noGrad. So I don't understand why he does it separate cases for training and not training.
I know when we use torch.noGrad, we are actually not calculating gradients. We are actually evaluating on the validation set.
Yeah, but he says if self.training, which means that we're working with the training set.
Yeah, in validation, you don't take gradients anyway, so that doesn't matter in validation. But you take the gradients in training, which is why he has to do torch.noGrad, because in this instance, you do not want the gradients taken.
Correct, yeah. I understood that part. You don't want the gradients if you're doing in the training phase. But what about this? Why? Okay, if you're not in... Oh, if you're not in training, you're saying that torch.noGrad is implicit.
Exactly. There's no gradient taken when you are in validation, so that's why you don't need that.
Okay, that makes sense. So let me just make a note there. Thank you. Oops. Okay, so that makes that part clear. So this is for the forward pass, and then once we've once we've updated the statistics, then we make this calculation. This is the actual normalization step, which you recognize from before. We're subtracting the mean, and we're dividing by the square root of the variance plus this parameter called epsilon. It's that formula that we were looking at before, the sort of the standard formula for normalization, except the only difference is that we've added this epsilon. And then we return x times, remember this was gamma in that formula, and this was beta. Remember he calls beta, he calls that the additive, the adds, which is basically an offset, which is like the bias. And then self.mults is the gamma, the multiplier. Okay, so this is explicitly computing the batch normalization step.
I have a question there, Joseph.
Yes.
So in the forward step, like you said, like if you start looking from bottom, you return basically x into gamma plus beta. The step before that, you're doing the normalization. My question is with the M and the V's. So in the training phase, he's returning MV is basically equal to self.update stats. And in self.update stats, if you look at M and V, you're basically returning the means that you calculated across the channels for one batch. Whereas when it's in inference, you're returning the exponentially weighted average means that you have accumulated till that phase. So does someone conceptually understand why you're doing this different means and variances for both of them?
Yeah, this is, okay, let's see. I didn't quite understand your question. You're saying that
Prashant, isn't it the case that because you have the lerp underscore that you're just updating the means and the thing in place, they are not different?
But in self-taught training, so basically the M and the V is the one that is changing between training and inference, right? In if it's self-taught training, you're saying M and V is basically self-taught update stats. And if you go back to update stats, M and V is nothing but just the mean for one batch across all the channels, and that's all you're returning. Whereas if you look at the inference phase, your M and V is basically self-dot means and self-dot vars. And self-dot means and self-dot vars is the linear interpolation of the M's and V's that you have calculated for all these batches till now, right? They're not the same thing that you're using for both of them. He talks about something about during inference, if there is a new image which looks kind of different from the previous images, you don't want to remove out stuff. I pretty much don't understand that part of it.
Yeah.
My notes say at inference time, he uses the running average mean and variance.
Right.
And
do you understand why that is?
Individual images mean and variance. Whereas you calculate the individual mean and variance when you are in training.
When you're saying individual, that is across a batch, right?
Correct. But then you use the running average across all batches, I would guess. I haven't looked at it closely when you do inference.
Yeah, do you know why that is? Like, it sounds pretty obvious, but I'm missing something over there. I don't know why. Is there a reason why you shouldn't be using the other one there?
Because you would want to average across all the batches, right? Why would you just use a particular batch, only that batch? When you're doing inference, you want the learning that has taken place across all the batches of the images, not just that batch, but you cannot, when you're training, know all about all of the batches. But in inference, by the time of inference, you have all of that information.
That makes sense. That makes sense. Yeah, to think more about that. But thanks, Srinivas, that was a good insight. Okay. Well, anyway, so that is the batch norm that we define. We basically built this batch norm from scratch. And then finally, he refactors this conv layer thing that actually builds all the layers for you by tacking on a if bn is true, that means you asked for batch norm. He's got this. So conv layer didn't used to have this this parameter bn, which stands for batch norm, but he's basically refactoring it to add an option to do batch norm if you put bn equals true. So that's what he does here. If bn is true, then you append this batch norm layer onto the end of each of the layers. And so that's the new version of conv layer. And I'm not sure why he doesn't export conv layer as well, the new conv layer as well, but he doesn't. This part, I wasn't exactly sure about how it all works. This initCNN seems to be recursive, and I'm not exactly sure how it works. And then if your model is, so it starts out here, if it says if is instance, if your model is an instance of this conv2D structure, then you do this. I don't know what F is. So
F is initialized below that. It's initCNN is calling initCNN underscore. Function below that.
Yeah, it's initCNN underscore is calling itself.
That's because you could have a module inside a module inside a module. So that's the recursive part of it, right? Every layer could have like a convolution layer within it. So you want to check for all the modules like that.
Okay.
But I'm saying the function below that is where initCNN and F is defined. So F is basically your chiming.
Chiming initialization. Oh, there it is, F. Chiming uniform. And I think it's, uniform is false to start with. So we're using the chiming normal that we talked about in previous notebooks. I'm not sure why I think they tried both and they found the results were the same. Although there were some reasons for believing that uniform should be better since it's less concentrated around 0. But in any case, they didn't get an improvement when they used uniform. So I think they're sticking with normal as the default. Get, learn, run. So then they changed this get, learn, run function to, let's see, why is it different than the previous one? So it has this, this learning rate layer. I think this is all the same as before. I'm not sure why they're.
You can pass in the uniform, which I don't think was an option earlier. I'm not 100% sure, but that might be because you can choose which initialization you want to pass in.
I see.
I think everything is same. It's just that you're trying to accommodate for this batch norm, right? Because like you were saying, if it's batch norm, when you add that beta term, it's nothing but like having a bias. So that's all he's checking for in if get attribute m comma bias none, then set m bias dot data dot 0.
Okay. If the model,
from what I remember, that's the only difference. Like, I'm not sure.
Okay, so if the model has if get attribute m bias none is not none, wait, get bias none, m bias. Does anybody remember what this get att function, what the third argument is?
If there is no bias in m, it basically will return none, right?
Yeah.
What is this none? Oh, okay.
Default
so, okay,
value.
there's no bias that will be returned. So if there's no bias, what this says then, as you're saying, is if there's no bias in your model, if there's no bias term, if it's not none, that means there was a bias, right? And there was a bias term, and in that case, you're setting all. You want to set all the. You want to zero out all the biases. Is that what your understanding of this is?
I'm confused now. Can you scroll up? Where is this bias as a? Is that one of the arguments that? No, I think.
I think model has an argument of bias.
I'm just trying to make sense from.
Okay, let's look for bias then.
So your cell 9, which you have, your Bn is equal to true.
Yeah. Oh, there's too many instances of bias. If get attribute bias.
So yeah, so basically here, and you're saying if Bn is equal to true, you want bias is equal to naught of Bn, which is false, right? So when you're setting batch norm, you don't want to add in a bias term because they're basically doing the same thing.
Yeah. So layers. So let layers equals this. So bias is an argument of nn.conv2d, right? And it can be either true or false. So this is saying that if bias is an attribute, that's what this means. If get attribute m bias none is not none, that means that bias is an attribute of this model, right? That it does have an argument named bias, and in that case, it's setting the bias equal to 0. M dot bias dot data 0.
Yeah, I'm not sure if that makes sense though.
Yeah, because bias is just a Boolean parameter. It's either true or false. So I don't get what this part is. M dot bias dot data 0 means.
I think the bias in 9 is basically just an argument there, whereas the bias that you're checking for in cell 10 is an attribute, right?
Yes, okay.
So you're checking.
But the get attribute means, doesn't this refer to this?
No, I believe it refers to m dot bias. So it is the model's attribute bias, not the bias equals parameter which we are passing.
Okay. M dot bias
is the same.
So m dot bias is not this.
No.
It's not this. Yeah.
No.
But what about, okay. And m dot bias is this, right?
Yes.
Is this? Okay. Okay, so we're checking to see
You're
if
checking if M has bias.
Has a bias.
Right.
And
if it doesn't, you'll return back none.
Yes.
So only if there is no bias, you're returning none.
Yes.
And
so,
is not none.
So if it's not none, that means that there is a bias, and then we're zeroing it, right?
Yes.
Yeah.
Okay. But we would only want to zero it if batch norm was true. I'm not sure where that comes into it. That is Bn. That is Bn should be true. In that case, we would want to zero it.
I think something else is happening in layers, right? When bias is not Bn, layers is kind of not creating that attribute, I guess.
If bias is not, I mean, if Bn is false, then bias will be true. I guess that I should look into what NN-conv2d means, but I would imagine that if bias is true, then it would create a parameter called bias inside of this model. I would think it would behave that way. And if bias was false, then it wouldn't.
I think that's what it is, right? So it's Bn is equal to true. So when you know batch norm is there, at the end of the day, you don't want a bias norm. So Bn is equal to true, bias will be not with Bn, so bias becomes false. So like you say, NN-con 2D is doing something where bias attribute is not non-existent. So when you go back down to 10 and you see if get attribute M bias, it doesn't exist, so it's none. So if it's not none, oh, there the logic breaks. Yeah, I don't know.
It's a little confusing, but anyway, we're sort of on the right track. This needs a little more exploration. So we're exporting these functions for later use, and this is an updated version of get, learn, run. I guess, let's see, maybe we can just see what the old version looked like. Run, okay. So the old version has inputs of, there. It has inputs of NFS, data, LR, layer, CBs, opfunc, uniform. It's got the same inputs. Let's see, how do we get the actual, do I just do Shift Enter to get the actual code? No. There's a way to look at the, is it double
question marks?
Double question mark?
Yeah.
There we go. Get, learn, run. Okay, so to compare, model get CNN data NFS layer required. CNN model uniform. Return get learn. It looks the same, or maybe that's because I've already, yeah, I think I've already run this, and that's why it's, so maybe we can look at the previous one, 6. I think it's defined in here, I think. Let's see. I just want to see what what we're changing here. Here it is. So this is the previous one. Let's see how that differs. I'm just going to copy all of this stuff for now, just so I can temporarily compare it to what we have. But just for comparison, that's the previous version of get, learn, run. I'm just seeing what's different. Get CNN model data, quarks, CNN model uniform. It's exactly the same. So I'm not sure what is going on here. Init CNN.
I think the only difference is the bias thing. And now, yeah, I just kind of looked at that. So like we were saying, if Bn is equal to true, bias is equal to not of Bn, so bias becomes false. And we understand that if there is batch norm, you don't want bias. So then you go to get, so basically bias is equal to not Bn will not set an attribute. So when you do if get attribute m comma bias, bias doesn't exist, so by default it'll return none. So that is nothing but false. So it is not false, so that becomes is true. So hence you're going if it all the bias dot data 0. So you're setting all the bias to 0 there.
Okay. Okay, so it's only, so the only difference is, okay, where was that? Oh, what was that? Get there. Okay, so so I guess the difference is init CNN has been changed.
Yeah.
So the old get, learn, run is the same. It has the exact same code, but it's using a different. It's using this new init CNN function. that we've defined here. And that's the difference, I guess. Okay.
Right.
I'm going to get, that was just for comparison. So, okay, so let's move on. Okay, so now he's using Hook to get at the statistics inside the inside of these runs, and so what's being plotted along here is the batch number along the x direction is the batch number, and here we're looking at mean, and here we're looking at standard deviation. The left-hand plot is mean, and the right-hand plot is standard deviation, or yeah, or variance. I'm not sure which. What does it say? Plot S.
Yeah, I think the left one is mean. You want it to be at 0, so it starts out at 0. The right one is the variance. You want it to be at 0.
Yeah, right. And the first set of plots are just a zoom version looking at the first 9 batches, or first 10 batches, sorry. So they're just, these plots are just a subset of these plots. You can actually see this structure here, right at the beginning here. So this is the zoom of the first 10 batches, and this is all the batches. And again, there's this error that Prashant helped to point out last time, that it's computing, it's tacking on to the training batches, it's tacking on the evaluation batches, and that's what all this wiggly stuff is here. The evaluation batches we don't really want to see in this plot, so there wouldn't be all these wiggles if we did it right. In other words, only plotting the training batches, of which there are 90, I think there are 98 of them, and the evaluation batches, there are 10 of them. And so that's why you're seeing 108 things being plotted here, whereas we're only interested in the first 98 of them, which are the training batches. Okay. Okay, so then he just runs this with a high learning rate, and it works. So you get a good result. I guess that's the difference, is you couldn't go to such high learning rates before. I think he was using 0.4. And so here he's running 3 epochs, and you're getting like 97, almost 98%. So the next thing he does is saying, well, now that we've built our own version of batch norm, we can refactor conv layer now to include PyTorch's built-in version. I'm not sure why he wants to do that, but I don't know if the built-in version has something different in it, but I don't think it does. I think that the version that we built is the same. Anyway, so now we're going to use batch norm 2D. That's the internal version instead of the version that we built from scratch. And then he runs the same thing, and you get roughly the same result. Maybe it's a little faster. I mean, this is 6 seconds and this is 5 seconds. So maybe the internal version is a little faster. So then he adds the learning rate scheduler that we built a couple of notebooks back. And this experiment I haven't tried, but he runs 8 epochs and shows that, oh yeah, we get a much better result. But actually after 3 epochs, it's not that much better. So this is validate. This is 3 epochs, 9821, and here it was 9804. So after 3 epochs, I would say they're pretty comparable. I'm not sure. That doesn't convince me that the learning rate scheduler gives you an improvement. But to really know that, I would have to go back here and run 8 epochs and see if maybe it stalls out at 0.98 and doesn't get any better, even if you run 8 epochs. But we would actually have to do that. Well, let's try it. Maybe we can do the experiment without.
The other thing, Joseph, is that he's really pushing the learning rate up there to 2.
Oh, is that right? Let's see. That's right. He's pushing the learning rate up to 2. That's right, because I made this note. We find that we can go all the way up to a learning rate of 2 without crashing out. Maybe if we tried a learning rate of 2 here, it wouldn't work. Let's try that. Learning rate equals 2. Let's see if it allows us to do that without the scheduler. It's not supposed to take so long. There it is. Well, it works with learning rate of 2. But, oh, it's still going. Takes longer. It's getting up to 0.98 on the second epoch. And 0.9856. So I am not sure. So Jeremy's thing was that, yeah, we can get all the way up to a learning rate of 2 and we can improve our result. But I'm not so sure that, I mean, we just showed that we can use a learning rate of 2 here as well. It takes longer though. That's one thing. Because this was pretty quick. This ran through pretty quick. And if we did 8 epochs, I don't want to wait around. I don't want to make you wait around for the result, but it'd be interesting to do the experiment here. If we do 8 epochs, if we get all the way up to 0.988 like we did with the scheduler, that would be a good experiment to try, but I haven't tried it yet. Anyway, yeah. So let's see. Then he sort of talks about a sort of a generalized view of norms, and he says, all right, here we've defined a batch norm, which is averaging the weights matrix over all the examples in the batch for each channel. So we would get one value for each channel. Now he talks about a layer norm where instead of averaging over the batches, you average over the channels. And I think he makes a comment about layer norm. Let's see. No, I don't really understand. I mean, it's interesting from a theoretical point of view that, yeah, you can define these norms and you can find different sorts of norms. There's another way you can do it. You can define, this is called instance norm, where you're just averaging over one of the examples. You're averaging over all of the weights matrices in one of the examples. Or actually, you're averaging over, yeah, the weights matrix in just one example instead of averaging over all the channels. And then a more generalized version where you average over, instead of averaging over all the channels, you average over a selected group of channels. So you can average over these channels, or you can average over these channels, whatever group you select, you can average. And then he points out that this idea of a group, this is called the group norm. It can be generalized. A group norm can generalize if you take all the channels, then it becomes the layer norm. And if you just take one channel, it becomes an instance norm. So this is basically a general construct that includes both this and this as special cases. But the interesting thing to me is that he tries layer norm and it doesn't work. And then he tries instance norm and it doesn't work. So I don't understand why it doesn't work in these cases. And then he points out that instance norm was designed for the job of style transfer. You know, that's where, you know, you take a picture and then you take something like Van Gogh's famous kind of the style that he made, and you can take your own photograph and then have the style of Van Gogh transferred on it, so it looks like Van Gogh's self-portrait. You know, that's what style transfer is when it's applied to images. So for some reason, instance norm is usable when you do style transfer, but I have no insight into why it didn't work here. Yeah. So finally, I think we're almost out of time, but and this is probably the most important part of this lesson, but so far I haven't understood all he creates this, so he points out a problem when you want to do small batches. In particular, when you want to do online learning, you're just running it on one example at a time, so your batch size is 1. And of course, 1, if you try to take the variance of something that only has one entry in it, it's not defined, it's infinite. And so, and he says that if the batch size is small, then there's always, say if it's 2 or 3, there's always cases where all of the instances will be 0. and then your variance will be 0, and then when you divide by 0, things blow up. So small batch sizes are a problem, and that's what he first discusses. And then the Fast.ai team has come up with this solution called running batch norm, which they, from now on, they use that instead of batch norm. It's kind of an improved version of batch norm that that works well with small batch sizes. And I didn't really get an understanding of what all this is doing. He's changing some things. He's adding some features to this this computation.
At a macro level, all he's doing is taking the running average batch norms, which you would typically use in inference, which we were discussing earlier, and applying the same idea during training across batches, because you can always store and use. But when he does that, there's a whole bunch of other issues that crop up that he deals with, which is shown in this code. But at a level of abstraction above that, all he's doing is taking the idea of the running batch norm, which you apply in inference, which we discussed earlier, and shifting that idea to also using it during training. Remember the discussion of why using only M and V from a batch versus using the self.means, which is more the stored and the lerped average in inference.
Yes.
It's now reverting that idea back to the training part as well. That's
so you're saying
the
that
running average.
Yeah, so you're saying that during training, you can make use of all the data that you've seen so far, even though you haven't seen all the data yet.
Exactly.
You can still make use of all the data that you've seen so far.
Yes. So conceptually it's that, but then there's a bunch of issues that come about of debiasing and other things that he gets into that, for example, the batch size can vary between batches, so you have to accommodate for that. And then, debiasing, which is again a specific issue. So he tackles each one of those issues. There are like 3 or 4 of them. If, for example, your first batch is very close to 0, then you have to deal with that as a special case. So he deals with 3 or 4 special cases, which is the reason for all this code. But conceptually, it's shifting the idea of a running average into the training loop and using that. And that seems to produce better results even when you have small number of samples.
Thank you, Srinivas. That's really helpful to me. Now I can go back and read it, and with that understanding, I think, I'll look at all those special cases that he deals with. But yeah, I didn't get that out of it, so thank you for that. So then he basically demonstrates that now we solved the problem of small batches with this new running batch norm, which he redefines this conv thing to include the running batch. It's basically the same as before, except for now, if batch norm is true, we stick on each layer a running batch norm instead of a batch norm. So it's the same as before, except we're substituting the running batch norm for the batch norm. Then we run it, and he's doing with one epoch, you can get pretty good accuracy, 96%. And then he challenges us to see how well you can do in one epoch. And he, first he says this is how well we can do so far by using this learning rate scheduler. I guess so. This was 0.96 in one epoch, but now with the learning rate scheduler and going up to 1.2. I'm not sure what, I don't remember what this Skedlin 1.2 means, but using the learning rate scheduler, you can then improve your result to 0.97. And he says that it's possible to improve it even further by doing some experiments and playing with things. So that will be an interesting thing to try. And then we're done. So there, I think finished in time for people to go to the next one. If they, there's no, there's no CS, what is it, CS224 one? today. That's right. So anyone want to make any comments or questions or anything?
The other just point with the running batch norm, to add on to what Srinivas said, was that previously we were kind of trying to calculate the variance of one mini batch, and then trying to combine that variance with the other one by taking a mean. So you're trying to take like means of variances, which doesn't make sense. So the other thing that he uses is, if you remember, I think from one of the previous lectures, the other formula for how you take a variance is like expected values of x squared minus expected value of x whole square. So he kind of incorporates that concept also. That's why you'll see like sums and sum squares.
Yes. Yeah.
Yeah, so that is one of the 4 things that he needs to account for. So one is that. The second is the batch size can vary from batch to batch. So you have to now account for that when you do the calculations. The third thing is debiasing, which essentially says that at every point, don't let the current point overwhelm what you are, or don't let it weighting be too high. And
or is it the other way around? I thought debiasing was that if you do a normal linear interpolation, normal exponential average, you're always weighting the first term the most, right? So isn't debiasing kind of countering that?
Exactly. So you want to counter that, because if your first one is 0 for whatever reasons, then you could really get into a bad place. So you want to counter the fact that the first one has a disproportionate impact. That's the third. And the 0 is a special case, and the debiasing is the general case of overweighting. So he handles both of those. So those are the 4 special cases he deals with, or adjustments for those cases is what the code does.
So Srinivas, could you again mention what those 4 cases are?
Yeah, first is what Prashant mentioned, that is he changes, obviously, the formula. You don't take running average of variance. So the first one is using the expected value of x squared minus the expected value of x squared. So that's the formula. So he changes it to use that formula. That's adjustment 1. The adjustment 2 is the batch size can vary from mini batch to mini batch. The third is debiasing, which is counter the effect of overweighting the first sample, which happens in normal lerp. And the fourth is if your first batch values are very close to 0, then the result destroys everything. So he clamps values to be no smaller than 0 if you've not seen more than n number of items, n being 20. That's the self.batch less than 20 code that you see. So those 4 adjustments are things that he does in order to get the running average to work.
I see. Okay. X minus mean. And somewhere in there he talks about fitting. Somewhere in the lecture, I remember he talked about fitting for epsilon.
Yeah.
He said something that epsilon is something that that normally people use it as a constant, but it can be a hyperparameter.
That's a quick fix solution before you jump into running batch norm. Is basically the problem is, like you was talking about, if your variance is too small, basically since it's in the denominator, numbers blow up.
Yes.
Right, 1 by 0 is infinity. So the solution for that is, if you have 1 by 0 plus epsilon, you can control epsilon. So if epsilon, in this case, I think if it's 0.01, and you're taking a square root of that, so it becomes 0.1. So even if it's 0, the worst case you'll blow up to is like 10 times more.
I see. So you control it. Whereas the default was 10 to the minus 5.
Yes, exactly. Yeah. So the problem with that is, Jeremy says that there are a lot of instances when the variances are greater than, like you clamping it at 10 right now. So it can be greater than that. So you want to accommodate for that. And that's how kind of segue into running batch norm, which takes care of all these things.
I see. Okay, so at the end, running batch norm doesn't use epsilon as a trainable parameter.
I don't think we use it as a trainable parameter in either case. It's a hyperparameter.
Right. That's right. Yeah. So he goes back to the. In other words, he goes back to the default value, and he doesn't need to try experimenting with other values.
Right. I think that's what kind of ends up with that.
Okay. So it'd be interesting to see if I didn't have time to do that, but it'd be interesting to see if one can improve on his result with one single epoch. He got 0.97 something, which is pretty amazing. So anyway, yeah. So now we should be done. We're done with chapter 10, and yeah.
The one other quirk in this chapter that he mentioned, and I haven't really kind of played with it a whole lot, is this whole register buffer where you kind of automatically have the ability to shift data or these values onto the GPU.
Yes. So how did you? Yeah. So how did you play with it?
No, I, in the sense of, what if you didn't do it, or what effect it has, and would you have to, in general, which values do you calculate, use, or store in the self.register buffer in general? Whereas in this instance, he just introduces it as a way to move these values onto the GPU by using the self.register buffer at some place in this notebook.
That and the
yeah.
So that's all done.
Moving it to the GPU, and the other concept that I remember he was talking about was that you want this to be stored along with your model.
That's right.
So I think register buffer kind of helps you with that too. But yeah, I also haven't tried not doing it and seeing what happens. I believe you get an error. Yeah,
you get an error. But I mean, the greater question that I had was more of, okay, he used it here, but what's the general principle? I guess anything that you would want to move automatically, but then there's a bunch of stuff that it doesn't move automatically. So what caused him to do that for these values and not for many others?
I see. So what's the reason why he put these onto the GPU?
Yeah, I mean, I understand this at the simple level, why he would do that, but it's more the macro question of, okay, so in which cases do you, if you're playing around with other things, in which instances would you want it to be stored in the register buffer? What's the general answer to that question?
Yes, that's a good question. So in the previous version, batch norm, I think he just stores means and vars or something. Let's see, way back up here where he defines batch norm. Yeah. So here, all he puts on the GPU is vars and means. And
I don't remember. Sorry. I don't remember exactly, Srinivas, but I remember in lesson 10, if you look at the forum, there was someone who had tried around the experiments, and they were talking about, like, when you try to load the model back up using your state dicts, and that's where it kind of creates problem with your default epsilon values, something over there. So only that much I kind of remember. I don't have notes on that. But yeah, I think that's a good place to look at it.
Could you say that again, Prashant?
In lesson 10, if you look at the forum,
yes,
there are people who have tried experimenting. And from what I remember is that when you try to load this model back up during inference, these values, when you're trying to load them with, you usually use that state dict to kind of pull it back in. And that's where the problems occur if you don't use register buffers. Like, they hold on to some default values and stuff like that. So I'm just saying a pointer is that's a good place to look for some more info.
Okay, in the forum. So good. Yeah. So here he uses vars and only vars and means, and is that because he needs to use them and update stats, or yeah. So he's referring back to them in update stats, which is something that gets called quite frequently. So let's see what's going on. Remember what's going on back down here in running batch norm. Sums, squares, count. Again, these are all things that are being referred to in update stats, which means update stats is something that gets done frequently. So maybe that's the key, is that an operation that it has to be done quite a lot. For those operations, you want to put these parameters in the buffer. Put these parameters on the GPU, I mean. Sums, squares. It's definitely all the variables that are being recomputed or computed in update stats. That's what these are. These are all the things that are called later on, involved in calculations in update stats. So maybe that's why they need to be on the GPU.
Yeah, now that I've phrased the question that way, I think the answer could be anything that's associated with the model that you may not be wanting to take gradients and stuff, but which is associated with the model, meaning that you want to store with the model, you better put it in the register buffer so it goes to the GPU and doesn't give an error when the model is loaded back and you get all of that data back. Because the sum, squares, batch, count, step, device, all of that you would want to store with the model, but they are not parameters, so you wouldn't get it automatically otherwise. And that could be the general answer. Anything which is not a parameter of the model, but which you want to store with the model, you better put it in the register buffer so it goes to the GPU and can be loaded back along when you load the model back.
Right, I just pulled that from the documentation. I just pasted it in the chat.
You put it on the chat?
Yep.
Oh, great. Okay. That's useful. Okay, well, if there's anything else we want to talk about, this is a good time. Are people trying? Are a lot of people doing the other classes, the Fast.ai version of NLP or the Stanford version of NLP? Are you guys doing that?
I think the Fast.ai NLP one is closed.
Oh, it's done?
Yeah.
Oh. What do you mean by closed?
I mean, yeah, it's done. Yeah, that's what I meant.
Oh, okay. So the review, the one that
was hosting.
in it 27, I forget his name. He was leading that one, and they're finished with it.
It's been a while, I think, almost a month.
Okay, I see. Yeah, we're taking a very long time, a lot longer than I thought to get through this. Through this class.
I think the way we are doing it is in a lot more detail versus the other ones.
Yeah, I mean, because when I went through this class the first time, I just kind of ran through and listened to the lectures and maybe tried some of the notebooks, but it really wasn't an effective way to learn it. It didn't stick with me. But this way, we're trying to do it in detail, asking questions as we go along and trying to understand things. Yeah, I think you're right. This is a better way to do it. And
one thing is we have 10 more new lectures to cover now with the walkthrough.
Oh yeah, the walkthrough. Yeah.
Yeah. So it's like
it's gonna never end. But
yep.
But I think when he finishes this, isn't this Fast.ai version 2 that he's going to be done with it and then publish it or something like that? Publish it in an O'Reilly book and make it sort of permanent, not permanent, but I mean, it's not going to be
a lot more stable.
As much. It's not going to be constantly changing like the previous versions have been. Yeah.
Yeah, this is kind of the replacement for the Fast.ai course this semester, the walkthrough. There is no Fast.ai course, right, this time?
That's right. That's right. There was supposed to be one in September, but they're not doing it
Right.
until spring. Yeah. Yeah. So that'll be interesting. Is anyone trying out any Kaggle competitions in their spare time? I haven't done that either, and I really want to. And I'm waiting for when we finish this class to then, because then we'll have all the tools at our fingertips, and then it would be nice to try some of the Kaggle competitions.
I think after the walkthrough, I think Jeremy posted another notebook which you can use the Fast.ai stuff a lot more easily in Kaggle. I haven't gone through it, but I saw his tweet.
Is it specially for running it on the Kaggle servers, or is it just in general for running in Kaggle competitions?
Yeah, I don't know. That started off saying that it's a lot more easier to run the Fast.ai stuff in Kaggle.
I see. Yeah, because they did make it available. They did make Fast.ai, the Fast.ai library, available inside of the Kaggle kernels.
I see.
But it was pretty slow running on their servers. Anyway, that's where I'd like to go next is try to compete in a Kaggle competition, because just having read what people write about it, that's the time when you really learn, is when you get yourself involved in one of those and really, and I've done it a couple times, just sort of dabbling in it, not really devoting a lot of time. And I think it just, you learn a lot more when you just throw yourself into it and really keep going. Anyway, well, thanks everyone. I really appreciate the insights that you guys have given. Srinivas and Prashanth, really helpful to have your comments and as we go through this. And so the plan then next Saturday is to start with chapter 11. So have a nice rest of the weekend, everyone, and we'll see you next week.
Thanks for hosting the meetup, Joseph.
Oh, you're welcome. My pleasure.
Thanks, Joseph.
Thank you.
Okay. Take care.